right? So maybe we should begin, and because today there are numbers of topics to be covered, one of which is the way that you can evaluate the models. Another is the tuning method, the method that allows you to find optimal parameters, right? So we are going to take a look at the procedures that would allow you to identify the the best parameters that will result in the best performance of your model. And also issues about evaluations. There are multiple issues about that, like the way that you can plot the results as a table. It's so-called Confucian matrix, and then from that point you can use cost and benefit to apply to the Confucian matrix to get maybe the overall benefit of the model or the marginal increase in performance once you have the model to compare with, right? So that's what we are going to take a look today, and you may have already seen the post that I posted in the last yesterday, I think, about final exam. We'll use the class marker to do the final exams. I'm working on that in creating the exam, 60 of them, but you get to do 40 of them randomly based on that. So the exam types will be multiple choice, that's basic stuff, true false, some of that easy, true false, and the harder one, like multiple response, that you have to get every answer right in order to get the score for that. And what else? Yeah, that's the free text part that you have to kind of fill in the keyword, but I don't like that too much. So mostly it will be about multiple response, also matching, right? You have to match the response. So the hard part of the questions would be in terms of the multiple response and matching, because you have to provide a perfect match and perfect choose of the choices in order to gain the score there, right? Okay, so we should begin about our contents now. There are a lot of things to go through here. Okay, let me start sharing the screen. Right, today's topic will be about model evaluation and tuning, which concern with the way that you can evaluate the models. We have taken a look at the basic measurements that you can use in order to compare the model, like precision recall last time. I think when we had the lecture about classification. This time we will take a look in a closer look on Otters matrices that allow you to compare between models, and also the way that you can tune the model, right? Tune the model based on the grid that you define. We'll take a look at that. There's a function that allows you to automate the procedures. You don't have to write your own for loops. You can use this in order to achieve the task, right? Okay, so let's begin. The topics today will cover first Confucian metrics, right? And the measurements, specificity. There is a measurement about specificity, precision, recalls, and other measurements that you can gain from using just a function Confucian matrix. We will take a look at the statistical properties of those measurements and how does those represent in terms of the model effectiveness, right? And then we will then shift the focus to the popular technique called lift analysis. Lift is a measurement of the fold, the increment of the chance to find the target. So supposedly you have, for example, like 10% to find your customers if you randomly selected from the populations. To have the lift of 2 would mean that you have about 20% of chance, right? Improve from the randomly selection. So we will take a look at that, and then the technique that allow you to avoid overfitting. that allow you to test whether the set of parameters that you have are suitable for model construction or not, and that is called validation, cross validation. There are a number of techniques that allow you to do validation. We did that once in classification. We use hold out, right? Hold one part, use another part, right? Hold one part for training, use another part for testing. That is called hold out technique, right? We will now see Otter technique and the way that it allows to validate the parameters. And finally, we'll take a look at the methods allow you to do parameter tuning. Although the technique is has its own section, but basically this is just for loop, right? For loop to identify the best parameters. But in order to do so, you need to understand parameters of the model. That means you need to understand deeply the technique, the theoretical concepts of those techniques. Okay, let's take a look at each of these one by one. All right, so let's first build a model. I need to build a model and get some prediction out of that first in order to have results and use it in Confucian metrics. All right, so I'm going to use decision tree and bank data, and then and just doing this. All right, so let me switch the share here to, no, not that, studio. Okay, so I need to load library, reverse apart, and then what I need to do is to load data. Read.csv, that's the easiest one. Then data. I forgot to change working directory. CSV use separator as semicolon, I think. And yeah, I should have bank data, looks like this one. Then I'm going to separate them into train and test. Okay, bank data, train, and that would comes from sample fract of the bank data with about 0.6, and bank data dot test, and that would come from getting the index out of the row names of bank data train. So what I'm going to do is to use bank data underscore train and get the row name out of that and convert this into integer, and then subtract it out of the bank data. Right, so the same process that we so if you take a look at the bank data train, the head of the bank data train, what you can see is here is that it contains a number of indexes. I think the method itself skip the, I don't think this is a good idea. The method itself skip the row number. There aren't any row number here. Never mind. I thought it contains the index, but it's not, so I cannot do this. So let's make it this way using the same method then, right? Enrow here, and then enrow com 0.4, and then let's make this test index. Right, now we have the test index, and then use the bank data and the test index here, and this would be I see. Potential. No. Yeah, I don't know what happened there. So this is bank data test. Never mind. This is the correct one. And then we will have the minus here as the trend. So basically, I just sample the index and then select part of that to be the testing data, another part to be training data. And then what I have to do is to train the model apart using the y 2 dot and data equal bank data train. And I'm going to predict the results using the standard prediction. I'm not going to adjust the parameter yet. Using standard prediction of bank data underscore test and type equal class. So what I end up with are the predictions of each of the testing set. All right, up to this point. Okay, now let's go back to this. Okay, now we are going to put this result into table, comparing the variable res here with the actual y in the bank data test to identify the errors in predictions. So what we are going to create is called Confucian matrix. Okay, Confucian matrix. Well, you can see that I put actual here, prediction here. But they are actually, it doesn't matter. It doesn't matter. You can put the auto on the other way around. But basically, if we put it this way, we can create a grid and then put the point of prediction onto each of these grids. If the predictions are correct, and because you get like positive predict to be positive, and the actual classes are positive, then those points should belong to the true positive class. If the model predicted that the points should be negative, and they are negative, those points should be true negative class and true negative part here. On the other hand, false positive means that the model predict that this is positive, but the actual class is not positive. So you can think about this as if you have the medical test, and that medical test show up that you have the disease, but actually you don't have that disease, and that would be false positive. On the other hand, if the model predict that you do not have disease, but you actually have that disease, then that would be the false negative part. You can see that there are different impacts, if we think about the real world here, the real world there. It depends on the prediction, whether they are correct or not correct, and then we can have different construction of Confucian matrix. So let's take a look at what we have there. Okay, so how do we create this Confucian matrix? You can do it by hand actually. Okay, so if you take a look at rest here, these are the prediction. Now if we take a look at the variable bank data test and variable y, and these are a vector or an array of yes and no as well, right? So how do we create the Confucian matrix? Let me show you. Right. Okay. Let me show you. I'm going to use blank page. Maybe I need to let me stop this sharing for a moment. Oh yeah, I can put it this way. I can share the screen. Can I share the screen? No, not yet. Let me stop it here. And then yes, and then put it there. Share content, my bot. Okay, now let's create a Confucian matrix. Let's say that you have a the results looks like this, and this is the model prediction and the actual, and we have the results looks like this one. This one say label, let's say yes and no. Yes, let's say the actual would be no, no, yes, 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 no, yes, no. Put it like that. And then we have yes and no, no and no, no, and then yes, yes, and then no, and then no, and then yes. Okay, now let's draw a Confucian matrix. Here, this part would be actual prediction, right? The model and actual, and then say the model predict yes and model predict no. This is model predict. Let me refer. Oh, maybe I would do this instead. Model predict no, model predict yes, model predict no, model predict yes. Okay, now let's create a Confucian matrix. Is basically a cross tabulation of the results table comparing between the model prediction and the actual data. So now we have model yes, and then model yes, and then actual no. What do we call this? Right, model saying yes, the actual saying no. Say if the model saying yes is 1, it's like positive, and actual saying and then for no it would be negative. So what would this be called? So we have about 5 names: true negative, true positive. This would be false positive, false negative. So what should we call this? Model yes, actual no. Right? What should we call this one? Now answer. In which case should we call this situation? Correct, it's false positive. How about this one? Which one should we choose from the 4? Right, true negative. So now we create a cross tabulation of the comparison data. I see that you get the point here. Okay, so how many true negative predict no and no that we have? Let's count. So we have the first, I will put a tick here to check that I have already counted that. Here 1 and 2 of them. For the true positive, we need to have model predict yes and the actual yes. This one, this 2, so we have true positive equal to as well. How about the false positive? The false positive. False positive is model predict yes and actual is actually no. So how many of them we have here? This one, right? 1 and 2, right? Also 2. And the last one, the false negative. Right? We have this one and this one also 2, right? I did not intend to have this, but yeah, we end up with this. This is the well, let's have some more result there. Let's say we have y and n and yn. Yeah, have more result like this. Then that would mean we will have the yy here in n and yn to increase to 3. All right. All right. Now let's yeah. Would it be okay? Let me change a bit. I think I will make a change about this one. Let's change it to ny. So this become 2, this become 3. Okay. Yeah, not such bad. Never mind. Yeah, it should be okay. So the reason I'm showing you this, I put some tag here. This is true negative, true positive, false positive, false negative. The reason I'm showing you here is to show you also the way to calculate precision and recall, right? Remember, right? We have the accuracy. The accuracy equal true positive plus true negative divided by true positive plus true negative plus false positive plus false negative, and that equals 3 plus 3 over 3 plus 3 plus 3 plus 2, and that is 6 over 11. Okay, that is accuracy measurement. And for the precision, equal the performance of the model, right? Whether the model is precise in terms of exactness. So that is when the model predicts yes, how accurate the model is. So that would mean we have the true positive divide. So I have to tell you this, that when I work in this field, I did not actually remember that it must be TP over TN. I did not remember any of that. But what I can do is that I know that the model predicts yes and actually, because I know the comparison between them, right? And that is you want to have the measurements of how precise the model is. Then it means that when model predicts yes, how accurate it is. So I did not kind of remember it by heart that it's going to be TP divided by whatever. But I can, once I draw the Confucian matrix, I can derive the formula from there. It's always been this way for me. In whatever field is, you have to kind of work it up to get to the point there. So this is TP plus FP, get the precision. And that would be 3 over 2 plus 3 equal 3 over 5, which is actually 0.6, 60% precision. And for the recall refer to the ability to recall the positive cases. That means we have Y. We want to see how many points that can be recalled, right? Can be extracted out. That would be the true positive divided by true positive plus false negative. How do I know that it must be false negative? Just take a look at this, because we have this column. This column is the actual positive, right? Actually positive, right? And when I create the precision, I look at this column because we are talking about when the model predicts yes. And for recall, and the value would be 3 over 3 plus 3, which is actually 0.5, 50%. So this is how you create confusion metrics and precision and recall, right, on paper. Okay, so let's move on. We will now take a look at the code and how to create confusion metrics and finding precision and recall and Otters measurements using R. Any question about this? First, the way to create that, the confusion metrics. No? No, let's move on then. And here you can create confusion metrics using caret, right, in R. Caret has a number of functions that would allow you to build a confusion matrix from data. Let's switch to R. So I will load the library caret. Okay, then there are a number of functions here. I would suggest that if you want to know more detail, search for the website that hosts the library for carets, and there will be a number of functions and explanation documentations on that. And it's very useful that if you take a look at the details on what you can adjust, but understand the functions alone wouldn't help you in your life as data scientist. You would need to have a deep understanding in terms of the concepts. Right now, you are at the second year of undergrad. I know that some of these are quite a lot, and the concepts, some of them maybe a lot more advanced than you are currently at. But I would encourage you to look into the details. Right? For example, when you look into the detail of decision tree, you will now know what parameters affect what part in the model. And that will allow you to grow up in the career of becoming a data scientist, data engineer, machine learning engineer, and AI engineer, and then creating this type of stuff, right? Right, so yeah, back to the point, confusion metrics. You need to give it a number of parameters. Let's take a look. Sometimes when I do this is because I actually do not remember what are the parameters. Yeah, the format here, you need to give it the data and the reference, and then the positive class, and you have the mode that you can adjust. Let's go down here. Data is a factor of the predicted class. Right? The first one is the predicted class. The second one is the factor of classes to be used as true result. So I can put it here like this: res and bank data and test data side y and positive class. Why do I need to have positive class? There are a number of ways that you can create a classification model. You can create a for what we have been working on. You can see that the classification model that we try to create, the label here, can be thought of as a binary label, like we have yes and no, which can be thought of as 1 and 0, right, or positive and negative, right? This type of class is known as binary class. In binary class, the objective of the binary class is usually to detect, right? Is to detect class 1, like you want to detect customers that would leave the company, that would churn. You want to detect customers that would not pay or would likely to fail to fulfill the contracts. You want to detect websites that may contain fake news. You want to detect the patient who would likely to got infected with the disease, for example. So binary class, when you perform prediction, you need to provide it with the positive class. The reason is that you need to identify whether 0 or 1 is positive, right? Because sometimes it's not 0 or 1. It would be like yes and no. It will be whether this is positive or not positive. So it depends on the task. But basically, this would be a detection. You get 1 to represent. You get the positive class, and then you get the negative class, not positive class that you have there. So that's binary representation of the class. But the label can also be used in the representation, like you can have multiple class, multi-class. This would be the multi-class classification. Okay. The multi-class classification, in this case, you will have multiple class, like you have class A, class B, and class C. And then the task would be to select from these set of classes to select one that is most likely to happen. Okay, so what we want to select, that would be either it would be A or B or C, right? So that is the multi-class classification. In R, in Python, you use the same. When you want to build a model to do classification, you can use the same code to do either binary class or multi-class. Depends on why. It depends on the output. Yeah, maybe for R at least, right? For R at least you can use the same code. For Python, you need to have a little bit of tweaking there. But you can see that in terms of the evaluation metrics, binary would require measurements. Precision recall would be for binary. You want to detect the class 1, but for multi-class there will be Otters measurements, which for now we will just focus on the binary cases here. Okay. So we need to define the positive class, and in our case the positive class is the label yes. Okay, running it, you can see that I did not specify the mode yet, and the results look like this. You get the reference, and this is the prediction and the reference, and then it gives you the accuracy and 95% CI, no information rate, what are there, and p-value and kappa and magnemma, and then the sensitivity, prediction value, prevalence. What are they, right? And you may wonder. Now let's take a look at each of these and to determine what are the meaning underlying these measurements. So this class, yeah, the first part of this class, we're trying to understand this Confucian matrix function. Now let's switch back to the slide. Okay, so for the first part, right, Confucian matrix, you have already understand that. You have already seen that is actually the projection of the results comparing to the actual class, and then create certain types of prediction out. Now let's take a look at Otters measurements. Accuracy. Accuracy measure the percentage of the model accurately predict the class. That includes both positive and negative. So accuracy is TP plus TN divided by the whole thing. But sometimes when you have skew class, right? Skew class, what does that mean? Skew class, in the skew class situation, you may have the proportion of the class to be like 0.9 and 0.1 for no class, right, and for yes class. It can be in this situation. This is a skew class situation. When we talk about skew class in numerical sense, you may think of something like this one, a Confucian matrix that is the rightward skew, right? But in terms of binomial, or in terms of the categorical variable, skewness refers to the situations that you get one class more than the other class. And sometimes in real life, I would say in real life, in almost with all of the work that I have been doing so far, you will end up with the situation like this one, that the yes class that you want to predict is so rare. That's why you need machine learning to work the job. Otherwise, well, if it's not that rare, you can just let human do the job without having the model to dig in through the data. But since you have the rare class and they might associate with a number of variables, using models would be a good way there. All right. So when we have skill class, accuracy would fall apart because of what? Anyone? What do you think? Why, when you have skill class like the above here, accuracy would, using accuracy alone would be troublesome? Right. What do you think? Why is that the case? Yeah, give me some opinions here. Why using accuracy is not a good idea when you have skill class?
Sure.
Yeah, sure.
So because in the last lab that we use the bank data, accuracy is very good, it's 90%, but if you look in the recall, it's just a 30%. That means it's for predict in the positive.
Yeah, right.
So,
Okay, so why is that?
because accuracy is looking at all result, and if the true negative is a very good predict, but the true positive is a very bad.
Mm-hmm.
But when the negative is have a more data than the positive, then accuracy will be show a lot good. But if we looking more in the true positive, it will be a bad.
Thank you, Anon. This is a good opinion here. Right. Because accuracy would work if you have balanced class, like 50% and 50%. Right. That would work. Because, and when you are interested in both classes, that you want to make and like making accurate predictions for positive and negative are equally important, and then accuracy will be important. But in many applications, like in the bank data here, you want to predict, you want to get the list of customers that you would send the offer to. And in that case, true negative doesn't mean much, because what does it mean by true negative? Let's think about it more carefully. True negative would mean that you know that if you send the offer to the customers, the customer would not respond, so that you would not send the offer. But that would mean you wouldn't gain any money at all, right? You wouldn't sell, because that's the negative part. But in the positive, if you get the true positive to be a lot number in terms of the numbers, then you gain a lot more benefit there because you can sell, right? So in the skill class, in the class that is skill like this one, you can think it easily like this. Suppose that we make a model predict that every label would be no. Then we get 90% accuracy. Seems good, right? But actually no, because if you randomly sampling from the data, just select a part of data, you get 90% accuracy anyway. So accuracy does not give you a good result there, right? So let's take a look at another measurement here. There's a row called, let me skip to here, called no information rate. No information rate give you the percentage of the largest class. It gives you the probability of suppose that you randomly sampling from the class, what would be the proportion of the what would be the accuracy of that, right? You get about 88% for this one. So this would mean that if you say that every class would be no, then you get 88% accuracy. Now, if you compare no information rate with accuracy, you can see that there is only a slight improvement there, not much. Right? So the model improved the classification a bit, but not that much. All right. So now let's take a look further to this one. Right? This one is 95%, 95% CI. CI stands for confidence interval, right? That you have learned that in your stat class when you learn about central limit theorem. The CI here is calculated from the standard errors of the binomial classification. It's calculated from the number of samples and the probability. So if you think back in your statistics class and in the what is that statistic class, in the binomial distribution. In the binomial distribution, you can calculate the standard deviation of the binomial distribution by multiply p with q, right? If you remember, right? The mean is p times n, right? Yeah. So from that standard deviation, you can calculate standard error. And that is standard square root of standard deviation. Standard deviation divided by square root of n, and that gives you this 95% confidence interval by subtracting that and adding that to the mean, the accuracy. To the accuracy, you get a type of the confidence interval of this model if there's some randomness here, and this gives you if the confidence interval does not overlap no information rate, it means that the model is good, right? It means that the model, I should say that the model is not bad because it improves the performance a bit. So you can see that by just taking a look at accuracy alone doesn't work that way, but you need to take a look at no information rate, and then you need to take a look at the CI, whether this improvement is significant or not significant. And there's another measurement called here, if you test whether the CI overlap with the no information rate or not. There is this test, p-value, to see if ACC is more than NIR significantly. So basically you can look at p-value of this comparison or the CI. Both give you the same information. Okay, so if p-value here is less than, now we can talk about p-value, right? You learned about this already. It is really hard for me before the midterm, because you have to learn about the statistical testing and the significant level, right? Because you see that this value is less than 0.05, less than 5%. Right? And this p-value indicate the chance that the null hypothesis would be true. And this null hypothesis is that accuracy equal no information rate. And you can see that it has a very small chance. That means we can reject the null hypothesis. And then the results would be that, okay, accuracy is better than no information rate. That means the model is better than not having model. Okay, so this is how you can interpret the results in the second part of the Confucian matrix function. Right, let's move on. The third part is more advanced here. It's more advanced statistics, but we will just try to understand the measurements. The third part is the measurement called Kappa. Let me switch this to it should have like a functionality that can have two screens at once. That would be nice. Can I? But it has second content for the camera. Wait, never mind. I try that later. Right? We have this kappa. Kappa here is equal 0.45. What does that kappa mean? Let's go into the detail here. There should be some explanation here. Right, this magma. Never mind. You can just look at my. So just remember that kappa here we got about 0.45. and then go back to the slide. So in terms of this measurement, Kappa Statistics indicate is the comparison of the observed accuracy comparing to the expected accuracy or the no information rate, the random chance, the no information rate. So how does it work? In terms of calculation, kappas come from the observed accuracy minus the expected accuracy divided by 1 minus the expected accuracy. Okay, so let's digest a bit. What does this mean? The numerator is the difference or the marginal increase. Okay, so I will draw it out using this. I'll use this instead. Right. So the numerator here indicate the if you think about it carefully, this is the actual accuracy minus the expected no information rate. So this would be the I would say it's called maybe marginal increase in accuracy. So it indicates a value of the raw absolute value of the increase in accuracy comparing to not having model. So it's like having model would improve the accuracy to about this value. And what does it mean by 1 minus PE? This is actually, if you think about it carefully, 1 is like the perfect classification. PE is the level that you expect to have. So 1 minus PE would be the gap that you can that the model can reach. So I would say this would be the so if you think about this way, suppose we have a class like this one, and we have the proportion of the class to be like 80%, 0.8, and that would be the expected accuracy, no information rate. That means we have about here 0.2 for the models to increase the accuracy, right? So you can think about this as that part, the gap or the gap to work with. Right, so it's the proportion of the actual increase in the model. So you can think of kappa as the proportion of how suppose that this is the no information rate, right? And in terms of accuracy, your model can get to say 0.9. That means the model now achieve about half of the gap that is provided. So using kappa allow you to draw up the indicators whether the models achieve how much it achieves in terms of the gap that it has, right? So there are some measurement here. If you have about more than 0.4, it means that you get about moderate level, 0.4 to 0.6, moderate level. More than 0.6 is okay, it's good, right? So as you can see from that, if you kind of achieve and push it hard to upward, then it means that it kind of gives you good results there, right? So this is how kappa work. Any questions about kappa? That would mean that it would be difficult for when you have very skilled class, say you have a skill class of 5% and 95%. Just improve the model by 1%. That would mean 20% of the kappa, and that would indicate that okay, the model kind of closing the gap by 20%. So think about it as the closing the gap measurement for this one, like how much in percentage that it can close the gap, right? So if you are okay with that and our result is 0.45, means that we get about moderate results, and that is not surprising because we use decision tree. Decision tree is not that accurate. if we have time later on, I will try using like random forest and boost tree, and then and show you how you get the different result there, right? So let's move on. This is Kappa. Okay, and the another advanced statistics measurement here is called magnemma, right? Magnemma test for agreement. Okay, magnemma test has the null hypothesis that the prediction are equally well for all classes. That means if magnemma would be useful if you have multiple, in the case of multi-label class, you want to have all class to be equally well. Magnemma would measure, is actually test the, is actually a chi-square test, right? It's the basic, but we are not going to do too detail that. It is basically the chi-square test to test whether the results are equally well for all classes. Right? So think about having because if you want to do chi-square, you need to have cross tabulation, right? If we create Confucian matrix and then create cross tabulation of the Confucian matrix in terms of the performance precision of each class, then we can do the mathematics. So think about it this way: if this is significance, right, it means that they are not equally well. Some class is better detected than another class. Okay, and precision would be unequal for that. Okay, so this is magnemma test. Well, do we want this to be significance or not significance? It depends on the applications. For binary, this doesn't matter at all, right? Whether you detect positive class equally well with negative class, it doesn't matter. But in multi-label, in multi-class situation, this might be important, right? Because if you want all class to work well equally, you need to take a look at this value. If not, if that doesn't matter, then this value again doesn't mean much, right? This is magnemma test. Now let's take a look at Otters measurement. Let me switch again back to RStudio. We have Kappa, we have magnemma, and then we have a set of measurements. These are a set of measurements that come from, there are actually explanation in the help up here on how you calculate each of these. But let's take a look at what does it mean by sensitivity, specificity, and Otter value here, right? One by one. First, let's look at the prevalence. Okay, what does it mean by prevalence? Right, prevalence indicate the positive event. Right, it is computed from the detection rate, and you have detection prevalence. So let's take a look at the value here to gain more understanding about the prevalence. Prevalence is the positive event. So prevalent would means because the word pre well indicates something that occurred earlier, right? Think about it as the chance to detect, the probability that you would detect correctly. So this comes from the measure class. So prevalence is actually just like the proportion of the measure class comparing to the rest. So it's like no information rate there. So if we kind of switch to this one, we get the here, because positive is the is yes, we got prevalence of 11.5%, and this prevalence indicate the positive class. Okay, not majority class, sorry, not major class. I should correct this. Yeah, it's detection rate, the rate of true event. Then this should be the positive class. right? It should be the positive class that you want to detect, and that's come from true positive plus true false negative. False negative is like is actually positive divided by the whole things. Okay, this is prevalence. And there are other tools measurements. These are the sensitivity and specificity, right? What are they? Let's look at similar similar illustrations like in precision and recall. Right? Sensitivity and specificity. Right? Sensitivity is the proportion of positive that are correctly identified. So sensitivity is recall. Okay. Specificity is the true negative rate. If you take a look at that, specificity measure the proportion of negative that are correctly identified. So you can see that both are about correctly identify positive class and negative class. So sensitivity is proportion that positive case are correctly identified. If we take a look at this circle, you can see that the sensitivity is the recall. It's actually the semicircle here divided by the left part of the square. And for the specificity is actually the outside, right? The outside of the right square, right, the right part of the square, and divided by the whole right side. Okay, this is the specificity, the true negative, right, divided by the whole negative part. Okay, so in terms of simple interpretation, sensitivity would mean that you kind of not miss the point, not miss the if this value is high, would mean that you do not miss the relevant points. Right? That model can screen the data. Right? You want the model to be sensitive, right? Sensitivity comes from sensitive. Sensitive means that it can react and then screen the data. For specificity, it would mean that so if it is a little bit hard to interpret here. It means that the model should not mispredict. High specificity means that you get true negative and then you get less false positive. Okay, because if in order for specificity to be high, false positive need to be low. That means the model will kind of having low false positive. Okay, so this is the measurement of sensitivity and specificity. Right? They measure the specific of the model, that the model can actually predict in the multi-class classification, model can predict the specific class, not making errors in false positive. Okay, so these are the default of the Confucian metrics to show you sensitivity and specificity. But you can see that it is quite a little bit. This is part of the concept, but it is more difficult to interpret comparing to precision and recall. But these four focus on different things. Sensitivity and specificity focuses on the positive and the negative, the relevant in positive and the negative part, right? While precision and recall focuses on the just the positive class, making positive classification. How does it fare comparing to in terms of the positive classifications? While sensitivity specificity focus on actually focus similar thing, right? Because you can see that, well, sensitivity is recall. This is recall. And how about specificity? Specificity is actually you can see that it take so it means that high specificity means low false negative, false positive, right? But take on the true and negative part, so it relates to false positive there. Okay, that's it, right? And for our result there, we get specificity of 0.43. 0.43 means that we got the model can recall the output of out of the result about 43%, and the specificity is 0.96 if we look at this Confucian matrix. Is because in terms of the true in terms of the negative case, the specificity, how much you make the false prediction, right? The correct negative prediction, right? And this would be true negative, right, divided by the whole thing here. So there's a little bit of false positive here, and it would decrease the value of specificity down. So high specificity means that the model can predict that there are like less false positive in the model. Okay, next would be the positive prediction value and negative prediction value. Positive prediction value and negative prediction values are the probability. Let me turn this to laser pointer. Are the probability that subject with positive prediction truly have the positive class. Okay, we'll get to see the number later on. So it's the probability that's mean of proportion. Subject with positive prediction truly have positive class. Okay, so what does it mean? Positive prediction have positive class. Okay, isn't that precision? Right? Right. So remember the number there. So this is probability of positive prediction truly have positive class, and the negative prediction value is the probability of negative prediction have negative class. Right. So when you take a look at this, this is the rate that you get the the precision, right? If you predict positive, what is the proportion of it become positive? It would indicate in terms of the usage. This would tell you something like, suppose the model predict yes. Should we trust the model? Right. The higher the value is mean that we should trust the positive result here. Negative prediction value is something like, if the model is saying negative, how likely we should trust the test, the model. Think about it as the disease test. You go to see the doctor, and the doctor tells you that, congratulations, you got negative result. Would you be at ease or not? This depends on the negative prediction value. Or if the doctor say, sorry, you got we see that you got positive results, we need more tests. Or should we just say that you have that disease? Depends on the positive prediction value. Okay, now we go back to the result here. We have positive prediction value of 0.6. Why is that? Let's look at it here. Positive prediction values come from 902 divided by 902 plus 580. It's 0.6086, right? This number. Negative prediction value is this one. One predict say no, and this yes at 1194. Right, you get 0.928. So these two values would tell you that if the model say no, you can kind of be at ease here. Oh no, this is not about the this is not about the disease, right? If the model say no, then it would mean that, okay, you can trust about 90% that customer would not respond to this offer. If the model say yes, it means that there is a chance 6 out of 10 that it will be correct, but there's a chance that it would be incorrect, about 40%. Right? You can now know whether you want to send it to a lot of people or just small group of people, right? So these are the positive and the negative value. Prevalence, you already see that is the proportion of the positive class. Next would be the detection rate, detection prevalence, and the balance accuracy. Okay, detection rate. Detection rate come from is the true positive. This is important because in most of the case, true positive is like the thing that you want to look for. So detection rate is the number of true positive dividing by the rest. Okay, it would tell the probability or the rate that the true event is predicted out of the whole things. Okay, so think about it in terms of the data point. It would be how many data point you can screen out from the whole data set. Okay, so this is called detection rate. Think about detection rate this way. Detection rate is the number of COVID-19 cases that are detected each day. Yeah, about that. So we see only the number that is positive, test positive and having the disease, right? But there are also other people test negative, test positive, not have disease after verifications. So there are a bunch of people there. So if we see the detection rate, we will know what are the percentage each day that can be covered, right? Detection prevalence. Detection prevalence come from the true positive plus false positive, right? It means the probability of we say that from the whole cases in classification here, how many percentage that the model classify as positive, right? So I will repeat it again. From the whole data set, right, from the whole cases, how many percentage, what is the percentage of the proportion of the cases that the model say that it should be positive. Okay, so this is the detection prevalence. It means that if this value is high, it means that the model saying that everyone is positive. If this value is low, then it means that the model saying that only this proportion should be positive. This detection prevalence should be comparable to the prevalence. Okay, if it's much more, then it means that you want to screen a lot of people. If it's less, then it means that you want to screen only the sure case. Okay, and this is the detection prevalence. Let's look at the model we have. In our model, we have detection rate of 0.049. That means we can get the true about 5% of the true positive from the whole case. We get detection prevalence of 0.08. You can see that detection prevalence is lower than prevalence. When it is lower than prevalence, it indicates that we kind of screen only the sure case. The unsure case, we kind of disregard that. Do you know why that is? Can anyone give me the reasons that we get lower detection prevalence comparing to the prevalence here? This is because of the default in R, the default setting in R, and it results in this phenomenon. Any opinion about this? Give me some. Why is it the case? It's because of the threshold. It's because when you use predict like this one, the R actually use threshold of 0.5, right? Threshold of 0.5, while the probability to find the positive class is only 0.1, sorry, 10%. You use 0.5 to say that it must predict like 0.5 to get say that it is yes class, and that would make detection prevalence lower. So the way to increase the detection prevalence is to decrease the threshold. To decrease the threshold of the positive class, then detection prevalence will increase. Okay, and the last one is the balance accuracy, right? Balance accuracy is the accuracy if you have balanced class. It is come from the accuracy in positive and accuracy in negative divided by 2. Accuracy in positive class is the sensitivity, accuracy in negative class is the specificity, and divided by 2 you get kind of balanced accuracy. It tells you that if you have balanced class, this should be the accuracy that you get. So it means like performance of the model, you need to use balanced accuracy to say whether it's good or not. In our case here, we got balanced accuracy about 0.69, 0.7, right? So it's about that for decision tree, right? So from all of this, you can see that each part of the measurements have its own meaning, right? We get this value out. Right, and we have already discussed about this one, precision and recall, right? Recall indicate the proportion of positive, right? This is true positive divided by the whole left part of the square, right? True positive rate. False positive means that how likely the model will predict correct, and F measure is the balance between the two, right? Precision time recall divided by precision plus recall multiplied by 2 indicate the balance between two measurements. Okay, this is precision recall is good for binary classification, right? For not binary classification, it's not good, right? Because it would it detect only just one positive class, right? So to get precision recall, we can just use mode and change it to precision recall. I can put in here the mode. Then this will change to precision and recall and F1, and the rest are the same. All right. Okay. So we will see that precision is 0.68, recall is 0.43. Comparing to the earlier, we got this sensitivity 0.43, just like I said, this is like recall, and positive prediction value is 0.608, which is actually the precision. They are actually comparable in terms of measurements, and you can see that actually looking at sensitivity and specificity give you more detail, but you need to interpret it correctly. Right, let's move on. Okay, that's the case for Confucian metrics and the measurements. Now you can see that in the situation, it's a lot of situations, you will not have the balance class. That's why we need to have like specificity, precision, recall as measurements to deal with unbalanced class. In unbalanced class, the thing that we are interested in might be just a small class, and the normal entities are uninteresting. We want just to screen for the interesting part. That might be the defective part. We might want to target the customers. So in that case, we got a skew class, and there are rarity in the class distribution. So that means accuracy of like what we discussed earlier, 99.9% may not be important if the class is already distributed in this fashion. Okay. So how would that affect in terms of the data models? So in many cases, if you sample from the data, you might sample from the data as 50% and 50%, right? And then from this 50% and 50%, the model may perform like this one. Like model A may give you like false negative. Model B will give you like the false positive here. This is for balance class, but like this one for classification A, classification B. For this one, like say predict yes and actually not churn is actually like 200 here, so it is this class, this one. Comparing in the actual situation, in the actual situation, the skewness would be a problem. That is, the true population may be like this one. That is only 10% of a positive class. That would mean that the one that we saw here would be a lot smaller, while the one that we saw here would be a lot larger. Okay, right? So the above and the below here would mean different things in the real world setting. But let's say now, which one is better then, A or B? What do you think? Which one is better, A or B? Which one is better than which? So you can see that the errors in the real world would be different. Like this error would be larger than classification A would be larger than classification B. But to say which one is better than which is too early at this point. Why is that? Because the actual cost of false positive, this is the actual cost of false negative, and this is false positive. The cost of false negative and false positive might be different. For example, if the cost of false positive is low, like you just send SMS to customers, cost is like 3 baht, right? It's low, while the cost of false positive is high, like losing the customers, and that costs like 500 baht. Then model B, then model A, right? Making a lot of false positive might be better than model B, right? Because model B lose some customers, and in total cost benefit calculation sheet, A will be better than B. So it depends on the cost and benefit, not just in terms of the model performance here. All right, but I want to raise this issue that if the class are not balanced, then this situation will occur. Right, you get a different performance in different count, absolute count in terms of the case in the actual setting. And yeah, like I said, there are unequal costs as well, right? When you make incorrect classification, like when you make false positive, it might incur different costs, right? It might incur different impact. Like in terms of false positive, when the patient is wrongly informed that he has cancer when he does not, right? What would happen? Right? It would impact a lot. It would impact the cost that this patient would go through another test, potentially, to test that that he or she actually has cancer. So there will be like a string of multiple of tests. So there will be cost of another test. Or if the patient got treated, then that would be a worst case scenario, that got treated for cancer without having one, right? That's a problem. But how about false negative? False negative is the patient who has cancer but wrongly told that they have cancers, and this is a problem because that patient might become the situation, the condition might be serious later on. Now let's think about the consequence in COVID-19 case. In COVID-19 case, like you can see that the government I would say criteria for screening COVID-19 is quite wide. That is like you need to earlier you need to just travel abroad, and then you are PUI, the patient per person under investigation, right? Patient under investigation, right? You need to just like fit in some situations, then you got into like a potentially positive case, and that is actually quite a filter, because it will create a lot of positive, like a lot of people return without having disease at all, but because it's serious, a pandemic there. Why? Because if you have false negative, then it impact only person. But if you have false negative case, right? False negative case, that is a patient diagnosed with COVID uh, but not fall into that test. That means that patient, in terms of pandemic, can spread the virus later on, and that's a problem, right? You can see that different impact there. In terms of marketing, false positive means that you send offer to customer doesn't buy, and that might cost you the cost of marketing, maybe not much. In terms of false negative, you might miss some customers. Right? Customer want to buy, but you did not offer, and then and that's false negative, right? So we need to consider the cost and benefit as well, right? How to do that, right? The way to do that is, instead of just looking at accuracy, looking at precision and recall, we need to look at the expected value, of the outcome. This comes from the multiplication of the probability of that outcome and the value of that outcome, right? So you have multiple outcomes, then you get the proportion of that outcome multiplied by the value. The value should be like the outcome, the value of that outcome, the cost and benefit of that outcome, right? And then you get the expected value. Okay, let's look at some example here. Suppose that we assign each consumer with a class of responding or not responding, and then assume that customer can only buy the product from the offering. So usually the probability of response will be low, and then say that we have this setting that we create a model to predict, and then we got the probability out that this customer have like 20% to purchase. How do we calculate whether we should offer to this customer or not? We can look at the expected benefit. Expected benefit come from the probability of response multiplied by this is actually multiplied, sorry, so the dot multiplied by the value of responding, and then 1 minus PR is probability of not responding multiplied by value of not responding. You may wonder, how come not responding has value? It can have negative value. It can have negative value, mean the cost. So say we are the value of responding. If we get respond, we NR value if we not get respond. Suppose that if the customer not respond, we get VNR equals 0. If not respond in terms of that. So we have a little bit of cost benefit here, that the product costs $200. Product related cost is $100, plus the cost from marketing is $1. Means that for each product that you sell, you get the profit of $99, right? That means VR is 99. If we mail the material and customer does not purchase, we get -1, right? -1 come from not buying. So buying get 99, not buying get -1. Right, then we multiply this with the value. So multiply with the value here. So suppose PR is 0.1. Let me use this one. So let's say PR is 0.1. Then we have the expected benefit here equal 0.1 times 99. And then plus 0.9, 1 minus 0.1 time minus 1. So the value here would be 9.9, and then minus 0.9 equal 9. So that means if the chance of this customer buying equal 0.1, we can send and we would expect to have benefit of $9 here. All right. So this is how you calculate the expected value. That means for this customer, yes, you should send the marketing material to these customers. Now let's consider that we got the probability of responding equal 0.01. Now 0.001 then. If PR, then you get 0.001 01 times 99, and then plus 0.999 times minus 1. Then this is some minus value here. That means if you send material to this customer, expected benefit would be lost. It will be minus. That would mean that you should not send the material. You should target this customer, right? So instead of looking at probability alone, you can see that by considering expected value, you can use the cost and benefit to determine the chance and to make decision whether to target the customer or not, right? And then you can use this as well to compare the model, right? Which model is better than which, by looking at the Confucian metrics. We can use EV to do that. So from training the model and then test the model, we got this Confucian metrics, right? The one that we got earlier. And we can create this. We can create the, from this Confucian metrics, we can convert it into this one. What are these, right? Should I ask? In case that I come back here, I should maybe use this one. So the model predict yes, and it's actually positive. This is the true positive. Model predict yes, it's actually no, it's false positive. Model predict no, it's actually yes, it's false negative. I should put red there. Never mind. Yeah. So think about this as let me put it this way instead. I'll just give you example here. So for probability of y, comma and p is a joint probability distribution of y and p. So this is true positive divided by the whole thing divided by all, say true positive divided by true positive plus true negative plus false positive plus false negative, right? So this is this one, and for this PNN is the true negative and then true negative plus true positive plus false negative plus false positive, right? So this is the proportion of the case that belonging to specific classification class here, a specific box here, right? And then we can multiply this matrix with the cost benefit. If we know that, suppose we target and get we target and then actually get the customer here, what would be expected benefit? What would be expected benefit if we have true positive here, true negative here? What would be the expected benefit if we make mistake? That could be a loss, right? Negative or benefit. So we can multiply this matrix with this matrix one by one, right? Using P outcome 1 and value outcome 1 plus P outcome 2, value outcome 2, P outcome 3, value outcome 3, P outcome 4, value outcome 4. Multiply everything together, right? For example, this one can look like this: 56, 7, 5, 42. And then we can just count and then divide it by total for each of these, and we get the value of 0.51, 0.06, 0.05, 0.38. This come from this 56 divided by 110, 7. Oh, sorry, this is 110. 110, right? Right, 110. Yeah, and then you get the probability of yes and p, yes and no, right, and n and p, and then yeah, you see the point here. Sorry, this again, I make a typo here. This should be n and n, right? Okay. So we have the count and get the proportion, and then we can multiply it with the cost. Then this have to come from the consultation with business people, because you would know what is the cost, what is the expected benefit to gain for each customer, for each sales. You need to discuss with the sales team, you need to discuss with the sales performance team to know this. Business intelligent people to know this one, or you need to calculate this out from the data. So we need to identify the cost of each box. First, false positive. Suppose that in this case, it would be the making predict response but not respond. So the cost would be the mailing cost. This would be -1, right? For the false negative, predict not respond, and false negative is predict to not respond but actually would respond. Since no money was spent in this case, but actually you can think about opportunity loss, but let's say we do not think about that here, just think about this campaign only, then the false negative cost would be 0. True positive cost, offer and buy, this would be 99. True negative cost, not offer and not buy, is actually 0. Means that if you make true negative, there is no benefit at all, right? You just kind of end up with nothing. All right. So this is the cost that we have. Let's multiply this with the proportion that we got earlier in the earlier slide. So we have this as the cost benefit matrix. We have this, right, as the proportion. Then the EV would be the multiplication of the benefit and the proportion. And then you get the point, right? You can calculate that out. Just multiply this with this matrix and combine them. All right. So this is how you calculate the cost benefit of the model. You can use this value to compare between model. Like you have model A, give you this Confucian matrix. You have model B, give you another Confucian matrix. Which one is better? You can use EV to make comparison. All right. Okay. Let's calculate it a bit here. 0.51. Oh, never mind. I will just make up with a new number. 99 minus 100. There. So let me share this. Right. Say we have the cost benefit like this one. 99 minus 100. Predict positive, predict negative. Actually positive, actually negative. And then we have two models. Model version A, we got Confucian metric of this is proportion of the case. You get this is 0.2, this is 0.3, this is 0.3, this is 0.2. And model B, right, get this is 0.1. Let's say this is also 0.2 then, but you get this is like 0.5. This is 0.1, this is 0.2, right? You get different results out of this. So the EV would be different. EV from model A would be 0.2 times 99, and then plus 0.3 times minus 1, and then 0.3 times 0 plus 0.2 times 0. The value here would be 0.299, 0.2 times 99, and that would be 19.8. 19.8 minus 0.2, this is 19.6. okay, and for EV of B, and this would be 0.2 times 99, and then plus 0.5 times minus 1, 0.1 times 0.1 times 0 plus 0.2 times 0, and this is 19.8, and then minus 0.5, so this is 19.3. So from this result you can see that model B is better than model A, right? B is better than A, okay, in terms of the expected value. Okay, let's take a break for 5 minutes, and after the break let's take a break for 5 minutes, and after the breaks we will come back to the next topic, and that would be on the lift analysis, right? We will analyze the lift of the lift, means the proportion in incremental proportion of the chance to detect that positive class. All right, let's take 5 minutes break. Right after the break we will continue on this one. Okay. Okay, right, let's continue. The next topic is the lift analysis. We have seen Confucian metrics, applications of Confucian metrics, and the way that you can further calculate measurements, expected value from the Confucian metrics. Now, in machine learning models, when you look at precision recall, when you look at the rate, the value itself doesn't tell you much in terms of performance comparing to the random classification. Well, Kappa might tell you that, right? But in some case you want to analyze the some segment of data, some segment of customers, and then you want to measure whether that customers comparing to the general case, would that customer be interesting. In that case you can calculate the lift, like lift up refers to the proportion, the fold between prediction rate, the predicted rate, right, and the average rate. It refers to the chance to obtain positive class divided by the model divided by the chance to obtain positive class by random. Okay, if I were to write this in mathematic term, this would be lift would equal to P A given B divided by PA. Right, PA is the prior prop. This is the probability of a given model. So write it in formal sense would be PA given model divided by PA. Okay, we would like to see the chance of detecting A given the model, and with the chance of A alone. Right? So this is the lift of the data that we want to find. The value would tells you the chance, the fold of chance to find the result there. So how do we get the lift? To get the lift, you need to use the function lift. You can use that in caret. Okay, so that's a function called lift here in caret, which allow you to calculate lift. To do so, we need to do this. Say get the positive prediction accuracy, res p. This is the predict of the tree, and then train bank data, train test, and then obtaining only column yes. Recipe would look like this one, and then we can put it together with the actual class. Right? If you use data.frame and then say the probability that we want is actually the recipe, and the class y is the bank data test and y, and this data frame would look like this. It would pair the actual class and the probability so that you can rank the probability to see the actual class will occur. I will call this the lift result, and then create the lift object by using function lift, and then say y tilt prop of the data lift result, and the class that you want to detect is yes. You get the lift out. This would give you the lift object, and then we can plot the lift object. And if you want to say if you just plot the lift object, it looks like this. Okay, lift plot will give you the percent of the sample tested. What does it mean? It means that if you rank the data from low probability, from low to high, rank the data accordingly, and then for each of the percent, right, we divide it to, like, this is 10%, top 10%, top another 10%, top 20%, and then top 30%, and so on. And then for each of that, you calculate the lift. So this would be accumulated of 10%, accumulated of 20%, 30%, accum, and then you calculate the positive, right? Getting the positive case divided by all cases in the range. You get the proportion of positive case in that ranking. And then when you like selecting top 20, right, what would be the lift value? The lift value would be let's say this is P. Then you can calculate lift from P divided by P0, and P0 is the prior probability, right? The chance to get positive when you use the whole class, the whole data set. So this would give you lift plot here will give you that once you rank the data like this one, and then covering data for each of the percent there, what would be the percentage of the sample that is found? The percentage of sample that is found is from the total class would be right, it would be the if you have like 10 positive samples, what is the percent of that sample that is found? 10 of the positive sample. Well, let's make calculation later in the another one. But from this you can have this one. This is the lift. The lift here, the diagonal line here indicate the randomness. If you randomly select the model, you will get this out. But if your model is good, then you should have the line that is lift up above this line. All right. And to get the actual lift value, It's actually on the next slide. Let's do hand calculation on the next as well later. So to get the actually if you put it 60 like this one, value 60, it would mean that to get 60% recall, you need to take the 23% of data. Okay, so sample file is the same as recall, right? How many points you can recall from the total points, and 60 is 60%. So to get 60% of the positive points, you need to cover 23% of the top data set or the top percentile of the results. Okay, so you can use lift chart to do this. You can calculate the performance, the PA, to get the actual lift value at different coverage. You can use this ROCR and actually the package called lift. Let's install that. Right, and then use the library ROCR. Did I switch the screen? Yes. Library ROCR. And then we will create a prediction from ROCR, and then use the response and the actual class and the label ordering starts with no and then yes, and from this prediction, which will rank the data set, the result, and number of true positive, false positive. We can then get the performance in terms of lift by using the prediction, and then say I want to plot lift with the RPP, right, the rate of prediction, and we can plot the 12 lift, and this will give us this plot. This plot tells us that at about 1% you get lift of 7. Once you cover the data about 20%, you get the lift of about 4. That means you have 4 times higher chance to detect the positive class than usual, and then the lift would go down gradually. This graph would tell us that the optimal points to detect the results here would end up about this point. Right? We should cut about 10 something percent of the top prediction, and we get about 3 something lift, right, 3.8 maybe, and that is actually the best result, because the more you include the data in terms of the positive prediction rate of positive prediction here, the more you include the data, and the lower the lift becomes, right? You don't want the lift to reach 1. 1 means that you get the results equal to randomness, right? Randomly selection. So this is ROCR. I usually not using this. I would just use the above here, the lift in caret. And if you really want to calculate lift, usually I would just do it by myself, write my own code to do the lift there. But you can use the lift function in the top decile in library lift to get the top decile lift. Top decile lift will give you the top decile. It need to have like as integer, because it's need integer for the positive class, and it will be 1 and 2. You need to minus 1 there. Oh, or it changed. Oh, I see. $y. Okay, then you get the top decile lift equal 4.82. That means you get about, if you if we rank the data, right? If we rank the data based on the probability and the class, and then we rank from high to low, then we cut the 10% top, right, out, and then looking at this, then you count the number of positive divided by the number of positive plus the number of negative, right, and then call it P. This is the probability of, actually this would be P of yes given model, and then we need to use it to calculate lift, which is actually P of yes given model divided by P of yes. Okay, and then we get 4.8 something there, right? So this is how you calculate the lift, getting the positive by, if you reselect like top 10%, what would be the probability of detecting the positive class, and then comparing to the average one. Okay, and then we'll see whether this is good. So lift of 1 means that equal to random, right? Lift of 4 or 8, 4.8 means that this is like 5 times better than random. Okay, this value would be if it's high, then it means it's very good there. Okay, this is lift value. Okay, right, lift value. Any question about lift analysis there? Otherwise, we have the last topics to cover in terms of the parameter tuning. So simple explanation for lift is the what would be the better chance, right? The chance to encounter for the model to perform better than random, right? The higher the number, the better, right? The range of lift can be as high as it can, right? Starting from 1, right? Lift starting from 1. If you have value less than 1, just throw that model away. It means that it's worse than random. I don't know how it can be. Right? Okay. So let's take a look at the last concept here in terms of parameter tuning. Right? Sometimes when you increase the complexity of the model too much, like say decision tree, instead of using the depth of this decision tree of 8, you say use the depth of decision tree of 100. Right? Model would be big and it would have high performance in training set, but it can have you can be in this situation that you want to do like regression, and then you use just a line to fit in this curve, then you get in terms of underfit. That means the parameters that you have cannot capture the variations. Optimal fit would give you the result like this one, pass through the middle, right? But if you increase the model to be too complex, you can get into this situation. This is called overfitting. Overfitting occurs when your model kind of remember the results just for the training set, right? It is really good, too good, right? It's just like people, right? If you read the book, read my slide, and just remember my slide alone, when there are the situations that you need to apply, and then you cannot apply, that is overfitting, right? Overfitting it occurs often in machine learning, in deep learning particularly. It's the case that like the training error become really low, but the testing error would be lower up to a certain point, that it will be higher if you kind of become overfit to that content. So my suggestion for any exams is that you can study as hard as you can earlier, but you need to relax and to let the knowledge kind of stir up. Usually back then, when in my years, I would go to theater to watch movies. Right now you can watch Netflix, but if you watch Netflix too much, you will be underfit like this one. So be careful about that. right? So overfitting. How to deal with overfitting, right? There are multiple methods to do that. First one is called holdout. We tried this out already by separating the data into training set and test set. Then we use training set to train the model, test set to estimate the errors. The drawbacks of this is that you sometimes we do not have a luxury, or we do not have enough data points to do this holdout. So that's a problem. Like, you have too small data set to do holdout. Second one is you can be lucky or unlucky, right? You can be lucky or unlucky that you get unfortunate split, or you get a split that too good to be true, not really represent the data set, right? So that's a point as well. So you can, this is a drawback. Okay, so this is the first way, the first technique, right? Holdout technique. Second one is called random subsampling. Right? Random subsampling is the technique that you can split the data into multiple trial, and then for each trial here, you can randomly select part of that to be tested, and the remaining will be training set. And then that's it. That's randomly selecting part to be test set, and then training set, and then repeat. And the metrics or accuracy, precision, recall would come from the average of the result. So this is random subsampling, cross validation. The most widely used technique is called K4 cross validation. The reason is that this is simplest, I would say. Because what you did is to from the whole data set, you partition the data set into let's say into 4 parts, right? 1, 2, 3, 4, and then you each time you use one part. Like if I were to draw it like this, I would draw it like this one. You divide the data set into 4 parts, and then for each round that you use one part to test, and the remaining to train, right? And then repeat that k time. Okay, use k minus 1 part to train, and then repeat it k time, and then the result come from the average of the whole things, right? This is the K4 cross validation, right? This is the most popular technique, right? Because it's simple and it gives you good enough result. When you have very few data points, you can instead use up to this technique. This is called leave one out cross validation. You perform this experiment n time. You leave one sample out and then use the rest as training, right? The situation that you do this is when you have very few samples, when you have very few data points. Like in my case, I use it in my PhD dissertation because I work in speech synthesis, and I create a model to synthesize speech and then compare to that person how likely it would sound like. And in my case, I have about 10 speakers, and if I were to do cross validation, I would need to split 10 into each 10 speaker would have their own data set, their own corpus, like 1,000 of them, but I want to split based on speakers. So if I were to use K4, that wouldn't be optimal, right? Because K4 means I use 2 4, no 3 4. That would mean that each 4 would have like too few speakers there. So instead I use this, leave one out, like leave one out and then use the 9 remaining as training set and predict just one, and repeat that 10 times. Right, so this is when you have few data points, you have few in my case speakers, you have like few set of data that you want to test, right? And then the results come from, again, the average of the rest, right? And we use the cross validation, the CV, right? But actually there's method, the leave one out as well, LOOCV is also parameters in this. So in R we use the caret to do that. caret has this function. Let's switch to R Studio. This function called the train control. The train control specify the control parameters for training. Train control, and then we need to specify parameter for training. Say the method is CV cross relation 5-4. Let's say now that set is really small, so number here could be the full number, right? Let's call this the train control, and then create the training. You can train the model in caret using the method train if you want to do cross validation. This one allows you to specify the formula of the model, the data that you want to train, bank data train, and the method that you want to control the training, tr control equal train control. And the method that we want to use means the model that you want to use is rpart, and it will perform cross validation. It takes a while, even though this is a small data set. Cross validation would take times a bit because it need to repeat 5 times, training 5 times, predict 5 times. Then we get the model like this one, right? It will give you this, that it will say that okay, this model perform split 5-fold. Like each time it use the sample size at this these are the sample size of each fold, and you can see that the size here is less than the total sample size here because these are the training size, and it tune the model as for you as well. It performs sampling and then it tune these parameters. How does it know that it needs to tune this parameter? This is because in caret it would have certain specification that if you use rpart, then you want to tune CP. CP is called complexity parameters. Okay, the higher the values indicates the coarser the model. Right, the model will be more detailed, higher performance if CP is low. Okay, so this is the meaning of CP. Okay, in our case here, we get so it performs parameter tuning for us. Right. In our case here, we get the CP of 0.01, and the result would be about 98.9, right? And kappa is 0.38. Okay, so it say that the final value that the model we use is 0.01. Okay. Right, you get the final models that looks like this. This is the object, rpart object, the resulting rpart object. Right. If you use the model, and then the final model, this is the final rpart object. Okay, if you remember when you type the rpart object into the screen here, it will give you something like this one. You can plot the graph to see using rpart.plot. And then you can plot this one to see the result like that. Right, this is the results from model tuning. Okay. Right, the resamples would give you the prediction results, the accuracy of each fold. Right, in our case, if we type in model resample, we get this 5. This is for each fold. That is, each fold we have these values as results. You can see that some of that has high accuracy, some that have low accuracy. Okay, so it's the results of each fold, and that's it for cross validation. Right, now you can see that using cross validation, the caret has already tuned parameters for you. Right, you can specify directly which parameters you want to tune in case that you don't want it to be the inherent one, the one that is like in the inherent one, the one that is that caret assumed to tune. right? For example, for R part, there are a number of parameters to tune, right? Different library would have different parameters as well. For R part itself, it has this CP, complexity parameters. This indicate the complexity of the tree. The lower means the more complex, right? So we can specify directly into that. There's another parameter called min split. Min split indicate the minimum number of observations that must be there in order for the node to split. If you remember in decision tree, when you have the node, the decision to split is whether you have information gain or not, right? But you can decide if you get about 10 points, you can decide to not split, right? To let it be the leaf node in case that you don't want the model to be overfit. Right? We can tune that here. What should be the number of observation, minimum number of observation to split, right? If this minimum number is low, like 1, it means that if you have more than 1 observation, you can split. But if you set this value to be 10, it means that you need to accumulate to have a node with at least 10 observation to decide to split, and that would make the model more generalizable, right? The model to be less complex. Like we don't want the model to be too complex here. Okay, to tune the model, you need to create a tune grid in this. So here I use the CV, the same CV. Metrics here can be changed. You don't have to specify. It would assume to be accuracy, but you can use Otter as well. Let's say you can check that out later on. For this one, I'll just follow my you said that I use accuracy, and then I will specify CP metrics, right? The CP metric. CP would be, instead of letting it tune file itself, I will specify it to be 0.001, 0.002, 0.005, 0.007, 0.01. Say I want to tune it down to be complex, but I also at the same time want to test it together with the min split. And the min split, what I want is like 5, 10, 15, 20, 25, 30. And then I want to create a combination, right? Combination, what does it mean? Right? I want to cross between both. Like you have like 5 levels of CP. For CP, you have 5 levels. I want to cross it with the min split. And min split also have 6 CP. So that this is equal to 30 combination of parameter, right? 30 combination of parameters. This 30 combination of parameters would indicate the total number of parameters that we use. Okay, sorry, I forgot to switch the screen. Let me switch the screen. Here I specify the metric CP and min split, and then I'm going to create a tune grid. Use author name to define. I use this expand grid of the CP equals CP dot min split equal min split expand grid. Doesn't file CP. Forgot to run that probably. Expand grid. I forgot to run CP. Forgot to run min split. CP equals CP, min split equals min split. And then you get the tune grid look like this one. This is a tune grid, which is the combination between CP and min split. And then we will give this to the model, to the training, right? Model tune. This would come from train, and we will train y2 dot and data equal bank data underscore train, and the method we use are part metric equal metric that we want to use, accuracy, and tune grid equal tune grid, and TR control equal the train control that we have earlier. And that's it. Let's run. Tuning parameter grid should have column CP. Tuning parameter grid should have column CP. It does have column CP. Or maybe because it doesn't support min split here. Supports only CP for the train here. Maybe. Let me try it out. Yeah, and because the library for in caret support only tuning of CP, so I cannot create a cross tuning here. But for there are otters, I will show you later on. The library actually support otter function for training of otter models, which support tuning of otter parameters. Okay, let's take a look here. Model tune. You can see that the best results occur actually when CP is 0.02. Okay, not 0.001. That means the too complex one is not good. This one is better. Right now we can select this one 0.002 as the result. Right. So this is how it works in parameter. Again, this one as well. In this example, 0.02 is better. Right. This is how it works in tuning the model. You can do this, but I'm not doing that in my code here. But you can do this instead of doing the grid search. The technique that is called here, that what you do here is called grid search. You can do the random search. Random search would randomly adjust the parameters by random, right? By specify search equal random in train control, you don't need to specify the grid, right? You can specify the search equal random, then it would and then the tune length to be 20. Like this one or 30 or whatever the iteration that you wanted to tune, it would randomly adjust the parameters until it get the best one, right? Until you get the best one about here. You can see that it's actually better than the one that I got earlier, because this is 0.904. One I got is 0.902, a bit better, and it's more detailed here. Right, so if you get lucky, random search will give you results. Right, grid search give you like general tuning. All right, so this is all. You can see that being data scientist is not just creating a model and that's done. You need to actually start with analyze the problem, right? Identify the method to use with the problem, work with the data, apply mathematics and evaluation of the model, and later on may also make suggestions on the business action that need to be used in order to apply the model to use in the real world applications. Okay, and to do that we need to have a proper evaluation technique, with proper evaluation measure to do the jobs. And you can see that accuracy doesn't fit here. It's actually very simple, too simple to do that. We need a lot more tools to use here. And expected value allow you to compare the model. You can see that. And parameter tuning cross validation would make it harder to stuck at the local optimum, to stuck at the overfitting, right, and get you the model that can generalize. All right, this is all for today. Hope that this course data modeling would kind of open the world to you to do work in data science, to do work with AI later on if you want. So that's it, right? Any questions about the topic today? Please ask.
Yeah, teacher, can you teach about the lift again?
Sure. let's put it this way, right? I think the best way to show you is to actually make calculation. Let me switch it to whiteboard. Lift, right? Let's suppose that we have this data set. After making prediction, we get the actual class and the prop, and then probability is B, and then the probability of each value, right? Say this is 0.1, 0.6, 0.0, 0.9, 0.5, 0.2, 0.5, 0.6, 0.3. Okay, and then say we have the actual class of yes, yes, and then no, yes, no, no, yes, yes, no. Yeah, let's say the actual class are like this one, and then we have property that looks like that. How do we calculate the lift? Say the lift of top 5 instead of top 10 percentile, we will get top 5. Right, top 5 lift at top 5. Okay, to do that, we need to calculate the P yes. What is the probability of yes without model? Probability of yes without model is the count of yes divided by the total data point. Here is 1, 2, 3, 4. 4 divided by, so it's 4 divided by 1. 4 divided by 8, right? So 0.5. So you get about 50% lift. 0.5. And if we change that and then sort the data according to prop, that will be a little bit difficult. Downward, all right? Descending manner. So you have 0.9, and this is yes, right? I use this one. 0.8, this is yes. Oh, pity that we cannot have the paper exam. I will ask you guys to do this. Yeah, since we have the online exam, doing this is a little bit difficult. I can just ask you the number. Well, seeing you calculate it here would make me more satisfying than 0.6, no. 0.5, we have 2.5. Which one should we get first? Whatever. 0.5 and 0.5. This is 1 yes, 1 no. 0.4, no, we don't have that. 0.3, yes. 0.2, get no. And 0, get no. Right? So here's the result after sorting. Sort by prop. And then say we want to calculate the lift at 0.5. Then we get the top 5. Actually, it should be top 10% something, but we got only this many points, so I'll just use that. So get top 5, then we get P of yes given model at top 5 equals 3/5. This is 0.6. That means lift would be 0.6 over 0.5, and this is 1.2, right? The lift of 1.2 means that it raises the chance to find um, to find class yes by about almost less than 1%, 1.2. So it's more than um, more than more than random. But yeah, because another thing is that because the chance to detect class yes here is like 0.5, you cannot have leaf more than 2. Okay, because it would be more than 1. It's impossible. You cannot have leaf more than 2, because if you have perfect classification and you get 1, that means leaf of 2. So leaf of 1.2 in this case means something, right? It means that it's better than random. All right, this is lift. Is it okay? Right, I'm going to close this. Stop share. Right. Any more questions about this? Right. As you can see from the post that we will have exam on the allotted date from university. Right. I'm in the process of putting the exam into the systems. Should finish soon. I will post the link to the groups. Okay. It will be link based. You get one chance to do that in each because I will ask you to fill in the uh, the ID, right? You have one chance to do that, and then if you try multiple times, I will know because there will be multiple copies. All right, everything. Anything else? Like I said, there will be multiple choice, some yes, no, some matching. The hard one would be matching and multiple response. You may not multiple response mean that you have to tick all of the correct answers. What else? And yeah, and right, that one. And don't forget about the project. Okay, you have until 25th of May to submit the link to Google Sheet and report, right? You need to submit the report as well. Write the report to link to Google Sheet and link to the video and the report. Okay, the report Ing, should we submit the report to the LEB too?
I think I will let you upload the report with the Google form.
Oh, okay. So that would be nice. Okay, so Ing would create this Google form so that instead of submit the link alone, you can submit the report at the same time, and that would help. Okay. All right. Say this is not a perfect way to have exam. I know. Instead of having paper-based exam, now we need to have this online exam. It's cool, but in many cases, I cannot control, and there are loopholes and whatever. So I would trust you to do the right thing here. Okay, if you complain that corruption is bad, do the right thing here, right? And doing the right thing that might not get you into good results, but it's the right thing to do. So try to do the right thing. I will not. You can open whatever you want. You can open books. You can open the internet. Actually, because I cannot control you at that time. So do whatever you want, because my exam would not be in there anyway. And yeah, and that's it. What else? Right. If you have questions before the exams, ask TA or me about that. We will try to respond it as soon as we can. I will upload the video this weekend. All right. Any more questions? No? Okay. So you have comments on our class, just give comments to the systems, right? You get the evaluation, instructor evaluation with that file away. I actually read it and use it to subsequent adjustment of the class anyway, in the years. Other than that, let's meet again, like later. Like I said, right? If you like the work in data science, you like the work in AI, then there will be elective courses later in the later years about this, in coding in AI, data mining, optimizations, big data, deep learnings. So that there will be multiple parallel, right? Multiple disciplines that if you want to work in this field, you can definitely attach yourself to those courses, and it will allow you to enhance your knowledge. And I can guarantee that what we teach here is actually the thing that company outside trying to learn, because I am actually teaching them right now to learn these things. So it means that you have now actually have skills that we at BX have been conducting training course for outside. All right. So this is it. Let's meet again when the time comes, and you can follow the channel because I will post video into the channel regularly until things settles, becomes normal again, right? So if no more question, let's call it a day and see you again during exam. For the exam, in some of the classes, the faculties will, the lecturer will monitor you during the exam, right? The problem is that we will have the exam on the 12th. I cannot. So, and also there are hundreds of you. My Zoom account cannot accommodate that many people. So I'll leave it to you guys, right? You got 3 hours, 9 to 12 to do the job. Just do the job, okay? And after, actually, right after, that's not good. I should turn that off. I would turn the function that you see the solution off, because some of your friends will see the score as well. You will see the solution and then you can share. Right, I'll turn that function off so that after, actually there is a function that after the exam you know where you get wrong. But because this is the exam that everyone has to do at the same time, and I cannot do that. I cannot allow you to see the solutions before the time's end. So yeah, I will turn that off. All right, for fairness. Okay, so that's it. See you again next time if we have chance. Right. So for today, goodbye.